Good morning in Taiwan, and evening or in middle of night in somewhere else. And today we have Dr. Lucas Liuzzo from Space Science Lab at UC Berkeley to give us talk on the moon, the interaction of the moon in the Earth environment, cosmic environment, which is should be a very interesting topic because he's exploring a region where few people have considered so far, and using an advanced numerical method. And Lucas, he was graduated from Georgia Tech, and his advisor is Professor Simon, who came from Germany. So I was hoping that he would speak some German here. and then after Georgia Tech, I think he went for a short time to Braunschweig and work with people there. And now he's returning to to America, and then now he's you're a postdoc, right? Or research fellow, yeah, at the Space Science Lab, which is a very powerful institution, I can guarantee you. So Lucas, and I will give the floor to you.
Okay, great. So yeah, I'm here today to talk about the moon and its interaction with Earth's magnetosphere. And just to give you a little background for those of you who may not be too familiar, a magnetosphere is essentially formed by the interaction between some kind of magnetized obstacle and its plasma environment. In the case of Earth's magnetosphere, that plasma environment is the solar wind, or a CME, where basically the solar wind spews outward from the sun, and when it sees the Earth and its magnetic field, it needs to be deflected around that obstacle, kind of carving out this cavity in that solar wind flow. So for the case of Earth's magnetosphere, this magnetosphere is essentially somewhere around 10 Earth radii upstream into the solar wind is where it begins, and it extends around 100 Earth radii toward downstream. So the moon, of course, which orbits the Earth, is orbiting around 60 Earth radii. So for approximately a quarter of the moon's orbit, it spends exposed to the magnetosphere, the Magneto-Tail plasma. And Earth's magnetosphere essentially can be broken down, to first order at least, into three separate regions. The first is the solar wind sees the Earth and the magnetic field, and that solar wind plasma becomes shocked. And beyond that bow shock is what we call the magnetosheath, or other various boundary layers. So that first region is the magnetosheath plasma, kind of maybe I can actually turn on this laser pointer. Yeah, so this kind of magnetosheath plasma is comprised of that solar wind becomes shocked and forms that magnetosheath. Once you pass the magnetopause of the magnetosphere, which is defined by the pressure balance, you have essentially two regions in that Magnetotail. The first is the Magnetotail Lobes, and the second type of region is the Magnetotail plasma sheet. So as I mentioned, during its orbit, approximately 30-day orbit, the moon spends about a quarter of its time somewhere exposed to this magnetospheric, this Magnetotail plasma. And historically, a lot of the knowledge from Earth's magnetotail environment has come from one of two places: either spacecraft flyby missions, so for example, like GeoTail or Explorer, or direct lunar science, so spacecraft that have either landed on the moon or went into orbit around the moon. The tricky part about this and trying to understand more about Earth's magnetotail from these type of spacecraft missions are that in the case of flybys, the trajectories are so limited, they're not necessarily focused on the moon's position. So while they may cross 60 RE downstream in the magnetotail, GeoTail, for example, had an apogee, I think, of 100 or 200 Earth radii downstream. So there's really just limited data that we actually get in situ by the moon. In the case of lunar science like Apollo or Kaguya, some of these missions were just so short that the amount of time that they spent in Earth's magnetotail is itself just limited. So luckily, this kind of gap, at least as of 10 years ago, was filled by the Artemis mission. So Artemis was originally part of the Themis mission. It was a 5-probe mission that is orbiting Earth. And after about 5 years during its mission, 2 probes from Themis were broken off and sent into orbit around the moon and turned into the Artemis mission. So in total, these probes have already spent 15 years in space. They're still going really strong, taking daily measurements of the lunar environment. But they were introduced into lunar orbit in 2011. So at this point, we have over 10 years of data from each of these 2 probes. And each of the probes, P1 and P2, have somewhere around 24 to 26 hour orbital periods, with the closest approach on every flyby of between 10 and 100 kilometers, and Appaloosa, so at its furthest point in the orbit, almost upward of 20,000 kilometers, approximately 10 moon radii. So the focus of my study is then to kind of take this 10-year data set from Artemis to better understand the moon when it's exposed to that Magnetotail environment of Earth's magnetosphere. So specifically, we can use this vast data set over 10 years to understand kind of the long-term properties of what that Magnetotail plasma looks like, and how these different regions of the Earth's magnetosphere, again, just to first order the magnetosheath, the Magnetotail lobes, and the Magnetotail plasma sheet, how the plasma varies between these different regions. And we can also take this question and look further outward into our solar system and try and understand and compare and contrast how the lunar magnetotail and magnetospheric environment is similar or different to the magnetospheric environments of outer planet moons. So for example, in Jupiter's magnetosphere or Saturn. The next step after kind of understanding the more general properties of the Magnetotail plasma is to then take some of those observations from Artemis and study how the moon actually interacts with that plasma population. So for example, what type of characteristic signatures do we see as the moon interacts with that Magnetotail plasma? And again, we can take that interaction and try and compare it to what we know from other moons and from other spacecraft, to try and see how the moon's interaction with Earth's Magnetotail plasma compares and contrasts to some of the other moons in the solar system. So the first thing that we'll look at is, again, just this kind of more general picture of the moon's environment to try and understand these long-term properties of what the moon is exposed to during, again, approximately a quarter of each orbit. So what I'm showing here now on the left is data from an Artemis encounter of the moon over approximately a 10-day period that the moon spent within the Magnetotail. So again, this is all data from Artemis, from one of the probes, and on the right here you can actually see where the moon was located with respect to Earth and with respect to some of the average locations of what we expect for the bow shock and for where the magnetopods would be located. So just to also introduce you to this coordinate system that I'm using here, this plot here is GSE coordinates. So X is pointed toward the sun, Y is actually anti-aligned with the orbital position, and Z completes a set essentially pointing northward. So the first thing that Artemis saw during this very first, as it entered Earth's magnetosphere, or before it entered Earth's magnetosphere, at the very edges of this data set here are the solar wind plasma. So you can see the solar wind is characterized by a very narrow, cold and ion energy flux here, a strong anti-sunward, tailward velocity in the magnetotail, essentially a lower temperature. As Artemis, as I mentioned, entered Earth's magnetosphere and exits Earth's magnetosphere, it sees the solar wind population on either side. The next thing that Artemis saw is now after entering that bow shock, so it sees this plasma become shocked by the presence of Earth and its magnetic field, and is exposed to the magnetosheath plasma. So this is characterized by a slightly warmer temperature. You see this ion energy distribution is much broader here during these two regions than it is in the solar wind. We still have a strong tailward velocity component to that plasma. And the magnetic field here is a little noisier than solar wind. It kind of fluctuates here in these components. So Artemis during this encounter saw this again before encountering the magnetopause and after exiting the magnetopause. So this magnetosheath population is one of the types of populations in Earth's magnetosphere. The next thing that Artemis saw were kind of these sporadic bursts of what correspond to the magnetosheet plasma. And this is, the energy distribution is even broader in this case of the magnetosheet. One of the biggest differences between the magnetosheath and that plasma sheet is the lower plasma velocities that Artemis detects. And again, this is kind of less, it's a little more sporadic and less well-defined than that magnetopause plasma. And the final type of region that Artemis can see, or that the moon can be exposed to during a magnetotail crossing, are the Magnetotail lobes. And the biggest difference of the lobe population is that it's characterized by this extremely low flux of plasma, really low flux of ions and electrons, that at times even corresponds to essentially no or very minimal instrument counts into the instruments on board Artemis. The other thing that is characteristic of the lobes are this extended magnetic field in the tailward or earthward direction. So if you kind of picture what Earth's magnetosphere looks like, is those magnetic field lines are stretched so far downstream that they're essentially aligned or anti-aligned with this X component. So again, this is what Artemis saw when it was exposed to the lobe-like conditions. So these are essentially the three types of populations that the moon can be exposed to during a magnetotail encounter. So our next goal is then, now that we kind of understand what these populations look like, to take all 10 years of Artemis data to perform some kind of statistical analysis of these different populations. So to do this, we took 126 crossings of the Magnetotail, starting with the crossing in October of 2011 and ending with one of the more recent ones in November 2021. So over this 126 crossings for each of these probes, there's somewhere around 60 or 70,000 hours of Artemis data. So this really is just a huge data set that we have at our disposal to kind of understand the lunar environment. So again, to separate this plasma into different regimes, we can break it up into three main populations: the magnetosheath. We require in our data set that to define the magnetosheath plasma population, that the Artemis probe, or that the moon was located at least 20 degrees off of local midnight. So this 20-degree angle here, so this whole cone here is 40 degrees. You see that on average, the magnetopause is always located beyond that 20-degree range. So this is a good way to kind of exclude any type of magnetospheric plasma and restrict ourselves to the magnetosheath. And we also require that the average density is over 1 ion per cubic centimeter. So again, just making sure we're not pulling out data from the lobes or from the plasma sheet. To define Magnetotail lobes, on the other hand, we require that the probe is located within 20 degrees of local midnight. So again, kind of within this cone here. So you'll notice that this kind of cuts off some of the edges of the plasma of the Magnetotail, but this kind of also ensures that we don't accidentally have any magnetosheath plasma or even solar wind plasma that kind of bleeds into the data set. In addition, for the Magnetotail, we require that the magnetic field is mainly sunward or anti-sunward, again, along the X direction of GSE, again, because that Magnetotail is so stretched in the lobes. And we require that Artemis was exposed to this lobe-like conditions for some extended amount of time. And in this case, I'm using a 2-hour period, again, to avoid just rapid fluctuations in the field. And the third region we define for the Magnetotail plasma sheet, again, we require the probe is located within 20 degrees of midnight. And we also require the magnetic field to drop rapidly. So if you kind of picture what the Magnetotail plasma sheet looks like, it's associated with the magnetic field lines kind of turning around downstream of Earth's magnetosphere, which again would be associated with this rapid reduction in the magnetic field. So these are the three different regions that we'll be looking at and kind of the conditions that we're requiring for each of them. Just to give you an idea, if we look at the total distribution now of these three different populations over the 10-year Artemis data set that we have, immediately you see the magnetosheath kind of pops out right away, this blue-purple color. Again, we're requiring at least the probes are at least located 20 degrees from midnight. And you see that, especially further toward the edges of the magnetosphere, all of this plasma is characterized as magnetosheath plasma. On the other hand, for the lobes and the magnetosheath, sorry, the lobes and the magnetospheric plasma sheet. We see a much more even distribution located closer to midnight. There's still a lot of data here that we're kind of throwing out. This is almost 2/3 to 3/4 of the data set. But the rest of this data that is not characterized as either lobes or sheath or plasma sheet is, for example, associated with rapid flows that are signatures of reconnection, or just some other non-stationary events that we don't want to include in this analysis here. Okay, so if we take a look now at what Artemis actually saw, what type of plasma environments the moon is exposed to. As I mentioned, there's approximately, we have around 45 million measurements that Artemis has taken. What I'm showing here now is essentially there are heat maps of what components of the magnetic field that Artemis saw. So you can kind of take a point here on this heat map here, and you have some set for a given point of a Bx value in By, or in this case, Bx Bz, By Bz, that shows you what Artemis actually measured. And the colors here correspond to the percent of time that Artemis saw that component set for the magnetic field. So if I kind of zoom in here, you can see I've also included these contours, which correspond to order of magnitude spacing. The innermost contour means Artemis saw this set of parameters at 0.1% of the time per each bin. So if you were to integrate over this innermost contour, you would have a large number, over 90% of 90% of the amount of time that Artemis saw this component set. So here I've zoomed in on the Bx and By component. So again, the tail or sunward aligned component is Bx, and By is the orbital or anti-orbital component. And the most striking thing that you can see is this entire distribution in the magnetic field is kind of tilted. You see really well here at kind of the edges of these distributions that this is tilted by approximately 4 degrees, which is what this dashed line corresponds to. And that 4-degree tilt is actually associated with the aberration of the Magnetotail at the lunar orbit. So because the Earth is moving as it orbits the sun, the solar wind plasma doesn't actually appear radial. It's kind of tilted due to this difference in the orbital velocity. And that angle is on average about 4 degrees. And you see nicely in the magnetic field, even within the magnetosphere down tail by the moon's orbit, that this magnetic field is still affected by that aberration. If we look at the BZ component, so in this case, this is the vertical one. In addition to seeing BZ is really stretched out, so for a narrow range of By and Bx, BZ is really extended. But you also see that the average, or the most frequently observed component of BZ is actually slightly positive. And this is consistent just with the directionality of Earth's magnetic field. If you kind of were to draw out magnetic field lines from Earth, you'll see as that magnetic field turns around that BZ is on average northward. So we see this kind of 1 to 2 nanotesla shift in the Z component of the magnetic field. So this here is for every single measurement. So there's no filtering for Magnetotail lobes or plasma sheet or magnetosheath. But now we can look at what the distribution looks like for these different regions of Earth's Magnetotail. If we look first at the magnetosheath field, again, you see the strong BZ, the strong north-south BZ preference. And that is associated just with the IMF that drapes around Earth's magnetosphere, kind of imparts this BZ signature, this north-south component to the field. In Bx, we also see now that the field is stretched even further than this 4-degree tilt that I showed before. And this is much closer to a 45-degree angle that's consistent with the angle of the Parker spiral. So you can kind of see that Parker spiral imprinting itself into the magnetosheath field. If we look now at only data that Artemis obtained for when it was located in the Magnetotail lobes, right away, the thing that pops out most clearly are these 2 peaks in Bx, again, associated with this strongly tailward or strongly sunward magnetic field orientation. And these peak at around approximately a 10 nanotesla magnitude for that field. We also see in By and Bz that these other 2 components are nearly isotropic and centered around 0 nanoteslas in the Magnetotail. For the plasma sheet, on the other hand, on average, the magnetic field is reduced in magnitude, and the extension of each of these components is much smaller than for the lobes or for the magnetosheath as well. So on average, this tells us that the magnetosheath, the plasma sheet field is weaker than in the lobes or in the magnetosheath. We can take the same magnetic field components now, and instead of comparing to a second magnetic field component, we can compare to the density. And this top row now that I'm showing is, again, a comparison on the vertical axis of the magnetic field components, Bx, By, Bz, and on the horizontal axis is the density. And you can see that the peak, the most frequent observations in the magnetosheath, again, occur all at high densities. So this innermost contour is centered at a density close to 10 ions per cc. So again, this is a really high density region for the magnetosheath. If we compare to the lobes here or even the plasma sheet, we see that the average the average plasma density is at least an order of magnitude, if not 2 orders of magnitude lower than in the magnetosheath. And in the lobes, these measurements are, again, focused at either along or away from the sun direction, so positive or negative Bx. But these the most frequently observed densities are located around 0.1 ion per cc. So again, potentially 2 orders of magnitude less than the sheath. In the Magnetotail plasma sheet, these densities are shifted slightly higher, focused now around 0.2 ions per cc and extending up to nearly 1 ion per cubic centimeter. And again, in the magnetic field, you can see that each of these components are minimized. They're really focused around 0 nanotesla. So we can play the same game and now look at the velocity instead of the magnetic field. This first plot here is showing, again, these 2 velocity components. And what we see that pops out really well in the data from every single observation from all data points, again, no filtering for any of these different plasma regions, is that in Vx here, the observations are centered around 2 different peaks. One of them is at really low Vx velocity, so almost around 0 kilometers per second, slightly with a tailward bias. But you see a second enhancement that's located near 300 kilometers per second in the tailward direction. So this is, flow that's traveling down tail away from the sun that also kind of had this secondary peak in the Vx component. If we compare to the Vy component, at this second peak near 300 kilometers per second in the tailward direction, we see that Vy kind of forms this bifurcated, this kind of two peak structure down tail. And we can look at what this flow looks like in the magnetosheath and see that in the magnetosheath fields, this same feature pops out in the Vy component. So this is associated, again, with just the flow, the solar wind flow being deflected around the Earth. And if you kind of imagine that solar wind seeing the magnetosphere on either side of the Earth, either on the dawn side or on the dusk side, that flow is going to have some kind of component in the Y direction. And you see really well at this, again, near 300 kilometers per second in the X direction, the kind of directionality associated with the moon and the probes being located on dawn or being located on dusk. So that pops out really nicely, especially in Vy. If we look at the velocity in the Magnetotail, we see that the velocities are, again, kind of shrunk. The extent of each of these components is much smaller than in the magnetosheath or in all the observations. And you probably can't see it really well here, but there's a slight tailward bias in Vx. So on average, the tails are traveling the flows are traveling tailward, kind of anti-sunward, more frequently than they are traveling earthward. But what's interesting, especially at these higher velocities, is that there's still velocities and observations in the Magnetotail lobes that have really high velocities, upwards of 300, 400, or even 500 kilometers per second. And what this is associated with are reconnection regions and really fast jets of plasma that are streaming past the moon, either earthward or tailward, that's associated with some kind of reconnection event, either tailward or earthward, whichever opposite side. So what's interesting is that we see these kind of signatures of reconnection at the moon that have this tendency of being either closer to Earth or further from Earth than the moon. In the Magneto-Tail plasma sheet, we see the same type of feature, this kind of reconnection-associated velocities. But we also see on average that the flows are located much closer to 0 kilometers per second. So on average, these flows in the plasma sheet are reduced compared to the lobes, and especially compared to the magnetosheet flows. If we look at the same comparison now with density, you can see very well that in the magnetosheet, these high velocity flows are each associated with this higher density in the magnetosheet plasma. Again, centered close to 10 ions per cubic centimeter. And in VX, almost all of these observations are exclusively associated with this tailward flow. So again, this is the solar wind that's flowing past the magnetosphere obstacle. And again, in BY, you can see this kind of two-peak structure associated with the dawn and dusk side of Earth's magnetosphere. For the lobes and for the plasma sheet, again, we see similar features as before, the really low densities in the Magnetotail lobes, and slightly higher densities in the magnetosheet. But again, still these really fast flows associated with these reconnection regions. And what's interesting feature that we see only for the plasma sheet and not for the other two regions are that these really high velocity flows actually have a slightly earthward bias. So they have a slightly positive Vx in the sense that there's, these flows reach higher positive x velocities than they do negative x velocities. So if anything suggests that on average, the reconnection region is located slightly further downtail than the moon, so maybe somewhere closer to 70 or 80 RE downstream, that the moon more frequently sees these positive, these earthward flows than tailward flows for these high velocity events. We can also now, instead of looking at these heat maps, look at the data set a slightly different way. And what I'm now showing are kind of histograms normalized to the total number of observations for each of these regions. And these are each component of the magnetic field. And for the magnetosheath field, again, this kind of purple color, for each of these components, you see that it's centered close to 0 and kind of has a broad distribution that's spread toward positive and negative values. We can compare this, especially in BX, to the Magnetotail lobe, where again, you see this almost bimodal distribution, these kind of two peaks in either centered at around minus 10 nanotesla, so 10 nanotesla toward tailward fields, or 10 nanotesla earthward fields. And we can even compare that to the Magnetotail plasma sheet that again is centered near 0, but is much more narrower in distribution. So more frequently is closer to a value of 0 nanotesla than anything else. The other thing that we see that's interesting is, again, in the magnetosheet, you can see this clear plus BZ enhancement. So this component here of the BZ is more frequently associated with this northward, this positive BZ than southward, again, just due to the orientation of Earth's magnetic field. We can look at these same distributions now for velocity. And again, the magnetosheath pops right out. You see these really high tailward flows that in magnitude, the average value or the median value here in this dashed line even exceeds the highest values experienced in the Magnetotail lobes or plasma sheet. And we also see this kind of almost bimodal, this two-peaked structure in the magnetosheath flows, again, associated with the dawn and dusk VY components. Something else that you can see in the magnetosheath flows in VY, again, is the aberration of Earth's magnetotail located near the moon, in the sense that you have this kind of shift in VY against a value of 0, where these peaks in the negative VY component are centered near 40 kilometers per second, but in the positive sense are centered closer to 60. And again, this is just explained by the orbital motion of Earth kind of imparting this additional VY velocity component onto what the moon actually sees. If we look at the density and temperature, again, we see the magnetosheath is associated with these really high density flows. On the other hand, we have extremely low density Magnetotail lobes and a slightly higher density plasma sheet. And for the temperature, you see the plasma sheet temperature is really spread out as this really broad distribution, especially compared to the lobes or the magnetosheath plasma. Okay, so if we take a step back and just kind of summarize this first part of the talk, I've shown that the Earth's magnetotail plasma can mainly be broken down into 3 different environments, either the magnetosheath, associated with fast flows and high densities, the magnetotail lobes, which have the stretched magnetic field configuration that points either earthward or anti-earthward, and is also characterized by really tenuous, very low plasma densities. And the third region is the plasma sheet, which is somewhere in the middle. It has intermediate magnetic field strength, slightly higher density, and flows that are on average near 0 kilometers per second. So we can take this now and kind of try and understand and place the moon's magnetotail environment into the context of other outer planet moons. And what I'm showing now, instead of magnetic field or densities, I'm showing dimensionless quantities. So on the vertical axis is the Alfvénic Mach number, which is just the ratio between the plasma flow velocity and the Alfvén velocity. It tells you how quickly Alfvénic or magnetic perturbations travel in the plasma. And on the horizontal axis is the plasma beta, which is the balance between particle pressure and magnetic field pressure. And we see, for the case of all the data, the most interesting thing that pops out is this really high beta, high Mach number plasma regime. But also there's some other features with lower Mach numbers and lower betas that come out. And if we, again, break this into these 3 environments, we see that the magnetosheath plasma is characterized by this really high Alfvénic Mach number, high plasma beta plasma. And we can kind of look at ranges for a few select outer planet moons. This one here I'll draw attention to is Callisto, and this other orange one here is Rhea. And we see, maybe except for the most extreme events at Callisto or Rhea, that the magnetosheath plasma, at least in terms of Mach number and plasma beta, is really unique to Earth's magnetosphere. So the moon is really exposed to an environment that we don't really see anywhere else in the solar system. If we look at the lobes and the magnetotail lobes and the magnetotail plasma sheet, however, we start to see some environments that are closer to the moons of the outer planet that we can expect. For lobes, we see the lunar environment is close to what Triton, so Neptune's moon Triton, sees, or some of the inner moons of Saturn. And for the magnetotail plasma sheet, we see that the lunar magnetic and plasma environment kind of resembles what we see at Ganymede or Callisto or Saturn's moon Titan. But I also want to emphasize here that even though some of these dimensionless parameters are similar, just the obstacle to that plasma flow in the case of the moon, or in the case of some of these outer planet obstacles, can be entirely different. So for example, the moon doesn't have a very dense atmosphere like we would see it at Titan or Triton. And there's no magnetic field, or at least no global magnetic field at the moon that we see at Callisto or Ganymede, for example. And even just the dynamics of Earth's magnetosphere are completely different than Jupiter and Saturn. So for example, at Saturn and Jupiter, they have moons close to the planet that is continuously emitting material. For Saturn, it's Enceladus with its plumes, and for Jupiter, it's Io with its volcanic activity. And this new plasma that's being introduced into the magnetosphere really dominates that magnetospheric type of dynamics. And this is just not a process that we have at Earth. But either way, it's still interesting to kind of look and see that these environments can be so similar across, throughout the entire solar system. It's a fascinating idea. So we can take this now and kind of, I've given a broad overview of what the moon on average kind of is exposed to, the type of plasma environment during a typical magnetotail crossing. But now we can focus on, instead of the average properties, kind of individual events as a case study to try and see what type of features pop out of the moon's interaction with the plasma. And again, compared to some of these outer planets, and try and understand the data that Artemis actually sees. So to do this, we're looking at these 2 events, one in October 2012, and the second one is in June 2014. And that October date may sound familiar to people who've been paying attention closely, because this date is the same one that I've shown earlier. And we're just going to focus on this region here where the moon was located in the Magnetotail lobes to try and understand that lunar interaction with the lobes. We can also look at the, where in these heat maps the moon was located for these 2 events. And you can see the October date is really essentially very close to that most frequently observed type of plasma environment by Artemis. And the June date is close and maybe slightly more extreme, but still close to what Artemis on average and the moon on average sees. So the first day we'll look at, again, is this date in October. Up here I'm showing in the top left is the moon's position with respect to the Earth and the magnetosphere. So you can see it's located right down tail of the Earth. And on the right here is a zoomed in view of the moon with the two Artemis probes. So you can see P2 was located far from the moon. So P2 is able to give us a baseline of what the plasma environment looked like without any type of perturbations associated with the moon. And P1 we see passed through the lunar night side, through this optical shadow, and kind of swung around onto the day side of the moon during this encounter. So I'm showing here on the bottom now a couple hour stretch of the Artemis P1 data. And near 6 o'clock, especially in the ion fluxes, we see this interesting feature that kind of pops out at really low energies. And it's the strongest feature that Artemis saw close to the moon in this case here. In the magnetic field, we see it's mainly aligned with a plus X direction, so fields that are pointing earthward. And the flow, at least associated with this enhancement, had some minus Vx and plus Vy and minus Vz features. And the other interesting that Artemis saw was interesting feature Artemis saw was a ramp-like depletion to that plasma density. So during the encounter, at least through the solar optical shadow, that plasma density detected by Artemis continued to decrease. So if I kind of zoom in here on this first feature that Artemis detected in the shadow, this enhanced flux is associated with, or the ability to see this enhanced flux is because when Artemis is located in the moon shadow, there's no spacecraft charging. So normally during a normal amount of time, Artemis is in sunlight, and the photoelectron effect causes Artemis to have some type of positive potential. And this potential causes or prevents ions from being able to reach Artemis and being able to reach some of the instrumentation on Artemis. But as soon as Artemis goes into shadow, that effect stops, and we're able to maintain the spacecraft voltage close to zero. So unlike in the sun, what happens now is that ions, especially at low energy ions, they're not repelled, they're not reflected from the spacecraft because there's no voltage potential associated with that spacecraft. And this allows Artemis to effectively see these really low energy ions that normally might be repelled from the spacecraft. But since we're in the shadow, Artemis can actually detect this low energy plasma population. So what this low energy enhancement actually corresponds to is just the ambient plasma environment during this day, during this October 30th, 2012 day. The next interesting feature on this flyby happened when Artemis was out of the shadow and on the lunar sunlight, the moon's day side hemisphere, is that we see again this kind of flux enhancement at higher energies than the first observation. But we also see this is associated with a rapid increase in plasma density and a velocity that is perpendicular to the magnetic field. So you have the strong Y and strong Z component to that velocity. And this signature is consistent with gyration of newly ionized lunar ionospheric particles that become ionized, for example, by photoionization, see that mainly X-aligned field and start to gyrate before they're picked up and convected kind of toward downstream. But the signature is then associated with the moon's ionosphere. So we can take this day now and to kind of try and understand a more global picture of what the moon's environment looks like. Instead of just along a 1D trajectory, we can model this moon's interaction to kind of understand the global signatures associated with the interaction. In order to do this, I'm using a hybrid model. And it's hybrid in the sense that ions are treated as individual particles. So we solve the Newtonian equations of motion for every single ion macroparticle that we have in the simulation. And electrons, instead of being treated as particles, are treated as a fluid. So we kind of have a modified Navier-Stokes equation to solve for electron dynamics. And this hybrid approach allows us to On the one hand, balance computational needs, so we still have relatively quick simulation times on the order of a day or a week maybe. But at the same time, we're able to resolve dynamics that are associated with individual particle motion for the ion. So for example, large ion gyration or flow shear between different species. So it's kind of a happy medium between a PIC code and like an MHD fluid code. So we can take the Artemis observations during this day and input them into the hybrid code. And so just to kind of understand, again, the background environment, we have a magnetic field that's along the x direction. We have a velocity component that is, you can see up here, the angle between these two, that is mainly along minus x, but has some kind of tilt out of that. That x is a plus y and minus z component. And again, just to remind you here, I have the coordinate definition. So x is sunward, z is northward, and y is the opposite direction of the moon's orbit. So if we look at some of the features that we see during this interaction during this day, if you remember, Artemis was able to detect that really low energy plasma population as soon as it entered shadow. And the reason this happened is, you'll notice, because the lunar wake, the plasma wake, where plasma is absorbed on the ram side, the upstream hemisphere absorbed and creates this wake toward downstream. This wake is tilted approximately 20 degrees out of the optical shadow. So what this allowed was for Artemis to enter the moon shadow, detect this really low energy population of magnetospheric plasma, and before even seeing any signature associated with the moon's interaction. So this kind of, this burst here, which I have by the pink star, again, is just almost a fortuitous observation, just of the geometry of the moon's plasma interaction that really allowed Artemis to see this ambient low energy ion population. But you'll also see, as the encounter continued, as Artemis got closer and closer to the moon and entered deeper and deeper into the plasma wake, that it saw this kind of ramp-like density and plasma decreasing throughout the encounter. So again, this is characteristic of what a spacecraft would see flying through a plasma wake. And the signature is really important because, unlike in the solar wind, when we expect a really rapid flow of plasma to go over the moon and cause this wake that extends 10 or even 20 moon radii toward downstream, this type of plasma wake had never been observed or even really modeled to exist in the Magnetotail plasma lobes. So this is really the first type of observation of such a wake when the moon is located in Earth's Magnetotail. So this here is, again, just kind of a schematic of what I had explained. Due to the tilt of the magnetospheric plasma flow with respect to the optical shadow, this caused this kind of perfect region where Artemis had been exposed to the shadow, but not yet seen any signatures associated with the interaction, that kind of allowed us to see this plasma population that otherwise would be completely hidden to Artemis. If we now look at the second feature here, again, this kind of flux enhancement associated with the day side, we see that I guess this quality isn't too good. I don't know what happened there. But the Artemis trajectory here kind of passed right through the region of where the ionospheric plasma exists on the lunar day side. And again, we have velocity components that are consistent with gyration, along with the density enhancement that was detected by Artemis. So this black line and the solid lines down here are the Artemis data, and the dashed line are the model. And you see very good agreement between where the density enhancement was observed and also in the magnitude and direction of the flow, the ion gyration, the velocities. In the model, we have a slightly broader, at least in the y component of the velocity, than was actually seen by Artemis. But in the z direction, the north-south direction of that gyration, it agrees really well. So again, this is consistent with newly ionized particles from the lunar ionosphere. We can then look at the next day, this day in June, where the moon was also located in the Magnetotail Lobes. And you see, compared to the October day, the ambient plasma environment was even more tenuous, so associated with lower instrument counts, lower densities. This was a really, really quiet day in Earth's magnetotail for the moon to be exposed to this plasma. You kind of see the trajectories are similar. P1 again goes through the optical shadow and then swings around to the lunar day side. And P2 is located far enough from the moon that we can confidently say that any non-detection of a signature in P2 probably means that it was associated with the moon if we see it in P1. So again, if you look closely, we see kind of an enhancement here as soon as P1 enters the lunar shadow at this really low energy magnetotail ion population, again associated with just this kind of ambient low energy population that's likely located in the magnetotail near the moon, but that was otherwise at too low energies for Artemis to observe. And we see again, as soon as Artemis goes back on the day side of the moon, again, these signatures consistent with newly ionized particles from the lunar ionosphere. In this case, we're able to back out the background parameters for that plasma to plug into the hybrid model to understand the global interaction. But unfortunately, unlike the October day, the orientation here between the magnetic field and the flow velocity were nearly perpendicular. So you can see here that magnetic field is entirely along -x, and the flow is evenly spread between y and z. So because this magnetic field was perpendicular to the flow, that means that a lot of these plasma interaction signatures are located in the plane that is perpendicular to the plane containing U and B. And unfortunately, the Artemis flyby trajectory is essentially in this plane with the magnetic field. So Artemis during this flyby just missed a lot of these signatures associated with the interaction. So again, you can see here in the data, really the only feature associated with the moon that Artemis saw is this kind of enhancement in the fluxes and the velocities associated when it passed through the lunar dayside ionosphere. But nonetheless, we're able to model this environment and kind of see what Artemis could have seen if the trajectory were slightly more favorable. And this I'm showing here is the ambient plasma density. And you see that this dashed line here corresponds to the lunar optical shadow. And if you look closely again, I don't know what happened to the quality here of this figure, but there's this kind of density depletion here forming these kind of wings that extend from the moon. And what this is what we kind of term a plasma absorption wing. And this is associated with the fact that the thermal velocity of the ambient plasma, the particles in that Magnetotail plasma population, is so high that as they're bouncing along or traveling along those magnetic field lines, they approach the moon from one side and kind of form a shadow. The moon cuts out half of that ambient distribution, and that causes this kind of particle shadow or these plasma absorption wings to form on either side of the moon. And theoretically, this angle, given the thermal velocity and given the plasma velocity on this day, should form at an 80-degree angle with respect to the flow, which I've drawn here in this dashed line. And you can see that the model actually does a very good job of reproducing this theoretical angle. So for that same reason, that high thermal velocity of the plasma means that we don't see any type of wake associated behind the moon. Because even though absorption is happening at the ram side, so in this case from this hemisphere here up top, there's no wake located downstream because those particles can very quickly refill because of their high thermal velocities. If we now look at, again, the ionospheric plasma density, you see that the lunar ionosphere during this day should have extended very far from the moon, just associated with the direction of pickup and the E cross B direction. But unfortunately, again, because Artemis' trajectory was out of this plane, it just didn't really see any of these features. So what I'm showing here, in the dashed component of this this trajectory, is where Artemis was located below this plane, and the solid one is above it. So you can kind of picture this trajectory is tilted at this 45-degree angle from this plane, and kind of pierce through these two regions here. And the only signature that Artemis could have seen, and indeed did see, was a slightly enhanced density and enhanced perpendicular velocity component associated with gyration. But if, for example, Artemis was able to pass through this region, it could have seen this extended ionospheric outflow associated with the moon's ionosphere, something similar to like we see at Saturn's moon Rhea, where this ionospheric pickup and E cross B just pulls the ionospheric particles further and further away from the moon. In the magnetic field, we see, again, where these two regions, these plasma absorption wings were located. We see the magnetic field is enhanced, the magnetic field magnitude is enhanced. And this is just consistent with pressure balance, because the density reduces, the magnetic field is enhanced to kind of offset that pressure drop. And you'll also notice, if you look closely, again, I apologize for the figure quality, but this feature is not centered at the moon's center. It's actually centered around the moon's ionosphere. So because the ionosphere is mainly photoionization generated, the lunar obstacle, if you will, is kind of extended into this hemisphere you can see over here. So the magnetic field tends to drape around the moon and the ionosphere and is slightly offset into this positive X hemisphere of the moon. This is something that we also see, for example, at Enceladus, because of the south polar plumes at Enceladus causes Saturn's magnetic field to be draped around the southern hemisphere instead of around the equator of Enceladus. So we're showing here the same type of, maybe not the same, but a similar type of interaction here happening at the moon and Earth's magnetosphere. Okay, so to just kind of wrap up, so I'll leave some time for questions here. I've basically taken two different studies. The first one to try and understand what the moon's ambient plasma environment looks like in the Magnetotail. And the second one is how the moon then interacts with that plasma environment and what type of characteristic signatures we're able to see associated with the interaction. But the biggest takeaway here is that over this approximately 10 or 8-day period that the moon is located in Earth's Magnetotail, it's exposed to a highly variable plasma environment. So it sees plasma from the magnetosheath with really high velocity, high density flows, all the way, on the other hand, to the Magnetotail lobes, where the flow is an order of magnitude weaker, the density is 2 orders of magnitude lower than the magnetosheath. And yet we still see some really interesting features associated with the interaction with that plasma environment. Some of the most important things that I've shown with this interaction are that we do have, similar to the solar wind, we have a wake that at times can form in the Magnetotail behind the moon, associated with this interaction of the moon and the Magnetotail plasma. And we also have some plasma absorption wings that we see at some outer planet moons as well, that form on either side of the moon. The other interesting thing that I've shown is that we can use Artemis in kind of this novel arrangement when it's not in the sun, when it's exposed to the moon's shadow, to detect a really low energy ion or plasma population that otherwise is not visible to the spacecraft. This really low energy population could maybe be associated with terrestrial ionospheric outflow. So really low energy plasma that extends down tailward from Earth's ionosphere. It's kind of leaking out into the Magnetotail. It's tricky to tell with Artemis because it's hard to back out composition based just on the instrumentation there. But it could be something that's happening that Artemis was able to observe. And I've also shown that, even though the moon is so much further and exposed to this unique plasma environment, there's also similarities to what we see at Jupiter and Saturn's moons as well. So all this to say, the Artemis data set is a rich data set. We have a ton of data that we really should be using to explore more about the moon's environment when exposed to Earth's magnetosphere. And that's all I have. I'm happy to take questions.
Yeah, thank you so much, Lucas. I mean, I think it's very detailed, the description of what you see, Artemis see over the last, 10 years, right? The data set.
Yeah.
And a very detailed analysis. I admire the skill in data analysis.
Right.
Yeah, hosting all the data. Yeah, very.
There's a lot of it, and I mentioned somewhere close to 60 or 70,000 hours. If you just add up all the data points that Artemis has, it's a huge data set that we can do a lot with.
That's the way to go, to analyze every drop of data.
Yeah.
With the audience, any questions from the audience, from you? Raise your hands if you want to, or just unmute yourself and ask the questions in case nobody's talking. I can see Nishino-san. Are you there, Nishino-san? Yeah. Do you have questions?
Professor Ip and Lucas.
Right.
I enjoyed your talk very much. Thank you very much. I have actually several questions, and one of them is in the statistical study, when you categorized the plasma properties in the Magnetotail, around the Magnetotail, you might see a kind of low latitude boundary layer plasma properties. And so the kind of data may be excluded in the current statistical study. Is it right?
Yeah, so that's a fair point. I mean, if anything, we may have been even too restrictive on some of these kind of ways that we're categorizing the plasma. Mm-hmm. The boundary layers are essentially because we, for the magnetosheath, just say density is over 1. It's really our only requirement. Mm-hmm. So if anything, boundary layers that we can see are probably included into that one. They also probably explain why there is that, kind of a big gap in the, near midnight. A lot of that data was just thrown out because it wasn't tail-like or sheet-like. Mm-hmm. And, even on a single individual flyby, the problem when I share my screen is I lose everyone else, but I can pull this back up again.
Don't worry. Go ahead.
If we look at, this data from a single encounter, these colored things at the bottom here are what has been mm-hmm. pulled out and characterized by that data set. But you can see even, for example, in this region, if you look at the velocity, there's these really high velocity event of some sort that has this plus X minus X kind of going back and forth across Artemis. Mm-hmm. This type of thing is not at all represented by these more simplified categories for the Magnetotail plasma. But kind of mm-hmm. the idea behind this is to take a simple definition of essentially just the magnetic field and then categorize it based on what is lobe-like, what is sheet-like, what is sheath-like. Having said that, there's also probably a lot of other ways to categorize that that we're just kind of trying to do in a more simple way to kind of take like a first step in explaining what these environments are like at the moon.
Well, as Lucas, as you said, that the Artemis is almost like a very, very, very good geotail observatory, and going up to 60 wave radii. You said that you think that the recognition point must be over what's that beyond 60 RE.
Yeah, so this kind of actually goes really well into the previous question too, is that these filters that I have are not really set up to see things like reconnection at all. It's really just based on magnetic field. Mm-hmm. But the fact that we can see even these, for lobe-like or for plasma sheet-like conditions, these signatures that are likely associated with reconnection, at least to me, says that we should probably look at a lot of these events and try and do a much better study and see where the reconnection region is. Mm-hmm. I know there's a recent paper that came out. I don't know if it was Kaguya data or if it was Artemis data. It may have been Artemis that said, on average, the reconnection region is at least close to the lunar orbit. Maybe there's a slight bias, I think, earthward, but it's still similar to what we show, sees a lot of VX events with 300 or 400 or 500 kilometers per second flows and enhanced densities going toward Earth. And I'm definitely not a Magnetotail dynamic expert, but I think at least one way to explain that is with some kind of reconnection region more tailward, that the moon just sees that kind of jet shooting toward the Earth that's passing over the moon with this VX enhancement or positive VX enhancement. Either way, I think it means we need to look at this closer, and someone should take the Artemis data and look for reconnection events.
Okay, good. Any other questions from the audience? We still have actually not much time, 10 seconds or so. Seconds. Nishino-san, you want to ask another question? Just to pick your brain?
No, not now. No.
Okay, good. Lucas, thank you. Oh, here's
Someone raising
Liuzzo.
hand.
You have a question?
Okay, so teacher, can you hear me?
Yeah, we can hear you.
Okay. So so good morning, Professor. So my question is that because your slides inside has shows the Jupiter and the Saturn, their plasma structure is different. So one is a lobe and one is a shelf. So my question is that because these two planets, oh, it's a giant planet, and I think their magnetic field didn't have too much different, but why their plasma structure will be different? So this is my question. Thank you.
Yeah, so the biggest difference between Earth and some of these outer planets is that the entire magnetosphere dynamics at Earth is driven by the solar wind input, energy input. And at Saturn, and especially at Jupiter, that energy input is actually from Jupiter's rapid rotation. So Jupiter and Saturn rotate at about approximately 10-hour periods compared to 24 hours at Earth. And this fast rotation causes a lot of different just global magnetospheric dynamics that happen at Jupiter. So one example at Earth is we have the Dungy cycle of magnetic field lines reconnecting, traveling tailward, and kind of going back along the flanks of Earth. Whereas at Jupiter, we have something called the Vesaliunus cycle, which is generated by, again, this fast, rapid rotation of Jupiter that kind of causes reconnection to, not have that same Dungy cycle-like dynamics, but more of a dawn side reconnection region that is then kind of shoots into the dawn side of Jupiter's hemisphere. So even just these dynamics are different. Another big one is the mass and the plasma input by Io and Enceladus that we don't have at Earth. Earth's ionosphere may be leaking out into the Magnetotail, but nowhere on the same scale as the volcanic activity on Io or plumes at Enceladus. Having said that, we can pick out individual events, individual flybys or encounters at Artemis C that could be remarkably similar to some of the outer planets just based on the magnetic field orientation and flows and plasma properties. So really it's a highly variable environment. And if you want, you can almost pick out any type of scenario that you want that Artemis probably had a good chance of seeing.
Okay, so the second question is that because we know that Jupiter, their magnetic tail is very long, so their end is in the Saturn orbit. So if the Saturn their planet is moving into the Jupiter their magnetic tail, so is the Saturn plasma structure will be changed?
That's a good question. I would say yes, it's almost certainly changed somehow because now the solar wind already at Saturn is very weak. I'm not sure what Jupiter's Magnetotail would look like all the way to Saturn, but I'm sure it would somehow affect the overall dynamics of that magnetosphere. I mean, another interesting thing that has actually been seen by Cassini is Titan literally leaving Saturn's magnetosphere due to the ram pressure and the magnetic pressure of the solar wind during, I assume, a CME or something, where Titan, kind of went out of Saturn's magnetosphere. That magnetopause and that bow shock location came so close to Saturn that Titan was just located in the solar wind. I don't know what would happen if Titan or Saturn had coincidentally seen Jupiter's Magnetotail at the same time. It would definitely be an interesting thing to look at. But the Magnetotail almost certainly affects Saturn in some way.
Okay, thank you, Professor.
Okay, I think that if there are no more questions, I think that we can close the session. And thank you, Lucas, so much. And
yeah, thanks for inviting me.
And hope to have a chance to get you back. I see that you're pumping out papers like crazy.
I'm trying to.
So I wait another half year, and you'll have a lot more to say, and then maybe I will invite you back.
Okay, sounds good.
Enjoy your evening in Berkeley. Yeah.
Thanks. Yeah, have a good morning.
Yeah.
Thanks again.
Thank you very much. Yeah. Bye-bye.